I'm Reed, and this is Evan, and today I'm going to be showing him about metric spaces. Okay, so a metric space is denoted, it's a general metric space, looks like this. So this, the X is your space, so a space could be something like the real numbers, or the natural numbers, or the integers. It's just like a set of numbers, and they're well defined. And then this D is your metric. And a metric is a way of sort of defining distance between points.
Okay.
So, like, the metric you use all the time is called the absolute value metric. So if I take the real numbers under the absolute value metric, so this is my space, this is my metric, we say that the distance between x and y, where x and y are both real numbers, both in my space, is equal to the absolute value of x minus y. And that's my rule for my distance. So like, you know, if I have 2 points on a line, the distance will be the absolute value of the difference, which just kind of looks like this length, you know. Eraser. But you don't have to always use that rule. I mean, it's the most useful for a practical application, but like in 2D space, it's a good example. Say usually we'd use what's called the Euclidean metric between 2 points. And that's just the distance formula. So that's the distance between, say, x and y is the square root of x1 minus x2 squared plus y1 minus y2 squared. You're familiar with that, right? Okay.
Yeah.
But instead, if I didn't want to use that metric, I could use what's called the taxicab metric, which is where I look at the lengths of these horizontal and vertical lines. So I say that the distance is instead the absolute value of x1 minus x2 plus y1 minus y2, right? And that's just like, if I'm driving a taxi cab in some city and there's only streets going up and across, right? Then the distance from x to y, I have to drive on this street and I have to drive on that street. So my effective distance is this length plus that length.
Okay.
So, and we really won't be dealing with 2D space.
Okay.
We'll be dealing with numbers on just a straight line.
Oh,
This is just like
okay.
an idea. It's so you have an understanding of what it means to be in a different metric.
Oh, yeah, that makes sense. Yeah.
All right. Okay, so metric spaces need to satisfy 3 properties. So the first property is that a distance from x to y is equal to 0 if and only if x is equal to y. So that double arrow just means that if I know that this is true, then this also has to be true.
Okay.
And if I know if this is true, then this also has to be true.
All right.
So the
Yeah.
implication works both ways. Okay, second property. Second property is that distance from x to y is equal to the distance from y to x. Makes sense. And then the third property is called triangle inequality. That says the distance from x to z is less than or equal to the distance x to y plus the distance y to z. So if I had some numbers on a number line, x and z, I pick some other point, call it y is over here. The distance from x to z is going to be less than or equal to the distance x to y plus y to z, right? In this case, the sum would look something like this. It'd be, that long. Where if y is in the middle between them, then the sum is just going to be, this is going to look like that. You know,
It'd be equal.
be equal, exactly.
Mm-hmm.
So that's why it's less than or equal to.
That makes sense.
And it's called triangle inequality because you can, like in 2D space, if I have a triangle, physical triangle, the length of, say, this side will be less than or equal to the sum of these two lengths.
Mm-hmm.
So,
Yeah.
yeah, that's where it gets its name.
Interesting.
So, I must prove that all these work and you're familiar metric space, the real numbers, under the absolute value.
Okay.
So, let's check the first property. So the distance from x to y is equal to 0. So let's assume that's true. Absolute value of x minus y is equal to 0. Then this side is 0, so I can get rid of my absolute value. So I could say x minus y is equal to 0, which implies x is equal to y.
Mm-hmm.
So I get that side. Makes sense.
Yep.
And then the other way is actually pretty easy. If x is equal to y, then the absolute value of x minus y is equal to the absolute value of x minus x, which is equal to 0.
Mm-hmm.
So it goes both ways. And second property, absolute value of x minus y. I can say that's equal to the absolute value of, I multiply the inside by -1, right?
Mm-hmm.
So that's y minus x. So, like straight from the definition, I get it. It's pretty simple.
Mm-hmm.
And third property, triangle inequality. Oh, this is all making sense, right? Like,
Yeah.
Oh, okay. So you're a little quiet.
No, you're just proving it all. So like.
Okay, cool. So the third property, I'm just going to use a simpler form of triangle inequality, so it's kind of like circular reasoning.
Okay.
But I say the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y.
Mm-hmm.
So does it make sense why that's true though? Why that should be true, just with 2 variables instead of 3 up here?
Yeah.
Because if they're the same sign, then it's going to be equal, right?
Mm-hmm.
But if they're, say this is positive, that's negative, I'm going to have cancellation inside here, but I won't have any cancellation over there.
Right.
So this side will be greater. So what I'm going to do is say that the distance from x to y, or say the distance between some quantity x minus y plus y minus z
Mm-hmm.
is less than or equal to, and then I'm going to call this x, call that y.
Mm-hmm.
So I get absolute value x minus y plus absolute value y minus z. So this side looks good. That's the same as here. X,
Mhm.
y, z. This side I have a negative y and a positive y, right?
Yep.
So they cancel.
Right. I see
Okay.
where that's going.
X minus z. We're good. Okay, so we're set for the real numbers under absolute value. Everything's been proven. Now I can get rid of this. Now I'm gonna give you some notion of a ball. So a ball of round x of radius epsilon is equal to the set y and x such that distance from x to y is less than epsilon. Okay, so in this case, epsilon is just a number. It's just some number.
Okay.
And that's the funny backwards 3 symbol we use for it.
Okay.
X is just some point in our space.
Mm-hmm.
And this says that this is going to be the set of every y in the same space as x,
Mm-hmm.
so just some y, with the distance from x to y less than some number,
Okay.
right? So, like, in 2D space, I could say, pick a point X, right?
Mm-hmm.
Pick some epsilon, call it 2, whatever, doesn't matter. And if I draw a circle around here, then my
Okay.
ball is going to be all the points inside the circle, right?
Yeah.
But we're less than epsilon, so it won't actually include like the border of the circle.
Right.
Everything less than 2.
But like- But like if you had a point like way out here, it wouldn't be in there.
Yeah, no, the ball, this is not in my ball, but this point here is in my ball.
Yeah.
Okay. And I'm not gonna erase it yet. I can extend this to the number line,
Mm-hmm.
which is where we're living right now. One-dimensional space. Say, pick some point X on the number line. Then my ball of radius, say 2 again. Let's find 2, let's say, this point's going to be X plus 2. This point over here is going to be X minus 2. Then my ball is just all the points in between in here, not including X minus 2 and X plus 2.
Mm-hmm.
Okay. So, first problem for you, I'll leave this definition up here. We're going to be using the real numbers under the absolute value metric, so it's the one you're familiar with.
Mm-hmm.
I want you to find the ball of round 4, center 4 of radius pi.
Okay.
So what do you think that's going to be?
This is 1D, right? Or is,
We're living on a number line.
okay.
This is 1D.
So you mind if I'm gonna sit down actually.
Yeah,
to
go ahead.
make it easier. Okay, so we got the number line, right? And then okay, so let's just say this is 4, right? And then you got 4 plus pi, and let's just say 4 minus pi, right? Wait, what am I trying to like write out here? Just like
Oh, yeah, so that picture's right. But, so what would you call that? What, all the points inside between 4
oh,
minus
you
pi,
just
4
want
plus
like an
pi.
interval? Is that
Yeah,
what you
it's
want?
exactly, it's an interval. So, yeah, I'd write that in interval notation.
So not including these two
Exactly.
points.
Very
Is
good.
that
Yeah, that's right.
alright, cool.
Okay, I'm gonna take back over.
Alright, there you go.
Okay, so this is a pretty easy example because it's the same metric space you're familiar with.
Right.
Well, I can change the metric on you. So let's instead go with what's called the discrete metric. So my space is going to be the natural numbers. So
Oh, okay.
natural numbers and D for discrete metric.
Mm-hmm.
So under the discrete metric, I'm going to define, this better, distance x to y is equal to, and this is like the piecewise notation.
Mm-hmm.
So it's equal to 0 if x is equal to y, and it's equal to 1 if x is not equal to y. Okay, so this is a little bit weird because there's only 2 distances you can have,
Right.
but I have infinitely many points. So, yeah, it's not intuitive, but that's because, there's infinitely many natural numbers.
Mm-hmm.
So what I say, or what I like to think is going on here, is that I have some point x, right?
Mm-hmm.
And all the other points in the natural numbers are kind of circled around it, and they all have some radius 1.
Okay.
And then if x, the distance between x and x, because x is equal to x, is 0. And it kind of makes sense in my picture because they're
Right.
coinciding. And if I looked at some other point, call it y, then I could also draw a picture y, all the other points are around y with radius 1, and then maybe x is like over here with radius 1.
Okay.
Okay. So, this in mind, I want you to find the ball, say around 3 of radius 1. So,
Okay.
Yeah, this is not an easy problem, but I think if you look at the diagrams and think about it that way, it might help.
Okay, so the center point would be 3 then,
The
right?
center point is 3, and your epsilon is 1. So
Okay.
the distance, just based on the definition, the distance has to be less than 1. All the points less than 1 in distance.
Wouldn't it just be 3?
Oh, exactly.
Oh.
That's very good.
Can I just put 3?
Yeah, and then, well, in set notation,
Oh, yeah.
well, I can write it if you want. It's just, it's like a 3, and then you do the brackets around it.
Oh, right.
A set of 3.
Right.
But yeah, that's right. That's the right idea for sure.
Okay.
I'm
Yeah.
surprised you got it so fast. That's actually really good. All right. Now, I'm going to talk about structure. So we say that T is a subset of X
Mm-hmm.
is open if for all X in T there exists epsilon greater than 0 such that the ball about X of radius epsilon is contained in T. So this is like a mouthful of notation.
Yeah.
Not easy to interpret. But, so what this means is that if T is a subset of my space, so like in the real numbers, I could say it's an interval.
Mm-hmm.
That's a good subset. It's all contained in the real numbers. We say it's open, and I'm defining what open means. It's open if for every point in my subset, it's like, here's my number line, and say I have some interval, X is in my subset, then there exists some epsilon greater than 0, so that's just, there exists some number, could be anything, such that the ball about X with that radius is still in my interval.
Mm-hmm.
So that means if I like draw a little ball around here,
Mm-hmm.
this ball is still contained in T, in my interval, right?
Right.
And if I get like really close to the endpoint, I just draw a really small ball, as long as it's still contained.
Okay.
But like, let's say I do something like this. Say this is 0, this is 1. So my interval includes 0, includes 1, right?
Mm-hmm.
Then I pick the point 1 exactly. Do you think that would cause any problems if I pick 1 exactly?
Yeah. Because you can't go that way. You can only go that way.
Exactly. If I draw a ball, I don't care how small my ball is, it's gonna peek out of my interval just a little bit, right? So I'm going to prove that under the real numbers, or the real numbers under the absolute value metric, the interval from 0 to 1, not including 0 and 1, is open.
Okay.
So I guess I'll leave this definition up here.
Please
So,
do.
yeah, very helpful. So here's my interval, 0 to 1. And I'm going to mark 1/2 in the middle, just because it's going to be helpful later on.
Mm-hmm.
So my first case, let's pretend X is somewhere between 1/2 and 1. It's on this half.
Mm-hmm.
Then I want to find a ball around X so that my ball is always contained in that interval.
Mm-hmm.
So what do you think a good distance or a good radius should be for my ball, so that's always contained in there?
1 minus x, or no?
One minus x. Well, actually, 1 minus x would be this distance.
No, one because isn't
No.
x the center point of the
Well,
ball?
x is the sample. Yeah, I'm not thinking straight. 1 minus x is the whole. Yeah, you're right. Is the whole thing. Okay.
Oh, but that would include one
That would
actually.
include 1. Yeah. So that'd be a problem. And actually, it'd be a problem for every x you pick. So that,
Right.
you don't want 1 minus x. But you're close. That's a good idea. Okay, what's something that's less than 1 minus x? Because I just want my distance to be less than this.
1/2 minus x. Oh wait, no.
Just, you take 1 minus x and make it less than 1 minus x. That's a good thing to do to it.
I don't know.
Okay, I'll give you the answer. It's 1 minus x over 2.
Oh yeah.
This
there
is
you
what
go.
I do. And that way, like I had initially drawn, sort of half-wittingly, it'd be this distance. It's the average between x and 1.
Okay. Yeah.
So, let epsilon equal 1 minus x over 2. That's good. So, my ball for any x in general, I'm running out of space, but that's okay. Ball about x, I'm going to say radius 1 minus x over 2. And that's just equal to the interval x plus 1, or no, x minus 1 minus x over 2, x plus 1 minus x over 2. We're going on time. We're okay on time. And this simplifies. So I can say this is 3x minus 1 all over 2, x plus 1 all over 2.
Okay.
And I didn't just do that in my head already. I did it beforehand. You
Yeah.
trust me, that works.
Yeah.
Okay.
Yeah.
So, what I want to show is that for any x between 1/2 and 1, that this point and this point are both between 0 and 1. So let's start with this point here. Okay, so I could say 3x minus 1. Oh, let's not start with that. Say we know x is less than 1.
Mm-hmm.
Okay, so 3x is less than 3. 3x minus 1 is less than 2. 3x minus 1 on 2 is less than 1, which is perfect, because we want it to be less than 1. And we can do the same thing for the other point. X is less than 1, so 3, or no, not 3x. X plus 1 is less than 2. 3, I keep writing 3. X plus 1 over 2 is less than 1.
Mm-hmm.
Works. That's good. Okay. Now, you understand how this works, right?
Yeah.
So why don't you show that these points are both greater than 0?
Both greater than 0. Okay. So.
And actually, I think I sort of did the easier case for you, the more obvious case already. So
Wait. So
what do we know about x to start off?
x is greater than 0, right? Or no?
We know, well, x is greater than 0 because it's in this interval here, this half. But specifically, what do we know about x? We know something stronger than that, because we're picking x in this half.
Oh, it's greater than 1/2.
Yeah, exactly. It's greater than 1/2. That's what you want to use.
Okay. So it's greater than 1/2, right? So then, 3x greater than 3/2, and then 3x. What is it? 3x minus 1. Kind of cheating a little bit by using this, but
It's fine.
it's more than 1/2. Oh wait,
That's right.
is it? Okay.
Yeah. Just subtracted 2 halves.
Oh yeah. Shoot. Sorry. And then, oh wait. 3x. Oh, I guess it would still be in there then. Less than 1/4, right?
Yeah, exactly.
Okay. And that still works, right?
Yeah, cool. Because why does that work?
Oh, because you're still within
Yep.
this interval.
Yeah, it's because 1/4 is still greater than 0.
Oh, yeah.
So you could just write 1/4, which is greater than 0. Or, it works.
Yeah, it makes sense. And then, okay, so then same thing, x is more than 1/2. So then x plus 1 is more than 3/2. And then x plus 1 over 2. Oh, I guess that's still within the range, isn't it? More than 3/4.
Yeah.
Yeah, and that's still within.
Well, no, that's sorry, right. Yeah. It's still greater than 0. So
Yeah, it's still greater than 0, and we already proved this lesson 1. So
good.
Cool.
Perfect. Okay. So we've done that for that one interval between 1/2 and 1. So what do you think we should do next?
between 0 and 1/2.
Exactly. So do you want to do that? I can get you started if you're.
Okay, yeah, no. So I'm gonna erase all this just so
Yeah,
I
yeah. Let's go.
You have similar handwriting. That's something I've noticed.
Oh yeah. You can also erase the whole ball. Actually, everything other than the definition might be good, unless you just want to copy.
I want to keep that though.
Oh, okay.
Well, unless
Well.
like.
Okay, but this is okay. So we're using our radius. Before we used the radius 1 minus x over 2, right? So, say plop a point down between 0 and 1/2.
Oh wait,
Try.
that's not within there. We used this based off. It was on this side.
Exactly. So what radius do you think you should use now, if it's on the other side?
So it should be.
It's like the same idea essentially.
So let's just start up here, where we were. So 1 minus x over 2 for this side, right?
Yeah.
So.
So what was special about that point? 1 minus x over 2.
It was the average of these, so
Yeah.
between 0 and 1, so it's just x over 2. Wait, no. Yeah, isn't it just
Yeah.
x over 2?
Exactly. It's x over 2. That's
So,
perfect. And the average of x and 0 is x over 2.
right, so
So-
x over 2, and then from there, how do we get those? It's.
So, might want to write. Well, what's your ball going to be? If you know your radius, what's your ball?
So the ball is x. Oh, is that in the way? I guess that's fine. X over 2, right?
That's good.
So then, so I guess the largest point and the smallest point is the interval there. So, okay. Shoot.
Oh, I mean, if you want, you could just kind of copy exactly what I did for my interval. Like,
Oh yeah. It's just x minus x over 2, right? And
Yeah.
then,
there you go.
just so we're together here.
Sure.
And I'm not gonna have any room, so I'll have to erase this anyway. And then x plus x over 2, right?
Yep.
And then that's equal to, so what do we got there? 2x over 2. So, wait, that would just be x over 2 still.
Yep.
And that would be 3x over 2.
Perfect.
So then we gotta do the whole thing again.
Yeah,
right?
so maybe you want to erase
Yeah,
what I have up top.
yeah,
and
yeah,
just-
let's do that. Let's just. Just copy here. Alright, I'll just write this
Yeah,
one down
yeah,
here.
Yeah, you don't have to show
I
it
don't
work
have
again.
I don't have to show the work again. 3x over 2. So I'll start with. So x is more than 0, right? That's how we start it, and
Yep.
then
Still more than 0.
wouldn't that?
Yeah, no, that's pretty simple. Yeah.
And then the same thing for this one too. It's just x over is more than 0. Is it 3x over? Yeah, 3x is more than 0. 3x over 2 is and then we gotta do 1, right? So x is less than 1.
Okay, well,
Oh.
x is less than 1. That's true.
Oh,
But
x is
can-
less than 1/2. right?
Exactly.
Right. So x is less than 1/2. So then x over 2 is less than 1/4. And then x is less than 1/2. 3x is less than 3/2. Then 3x over 2 is less than 3/4, which is still within our interval here. So that
Yeah.
should be good, right?
Perfect.
All right.
I think that's it. I mean, we're at a half hour anyway, so
Yeah, we
perfect.
are. Perfect.